Good morning and welcome to today's lecture. We will continue our discussion on this functional dependency theory, which provides formalism for determining which are good database designs and why those are good, and if we follow these, what are the things that we can avoid, and if we do not follow, then what could be the implications. That is what we are trying to arrive at. And to recollect our discussion so far, we have talked about this basic idea of having, of course, our schema in first normal form, and that's why we can understand why, if we have multi-valued attributes, we cannot put, for example, multiple mobile phone numbers with the roll number in the same column of a table, because that would have violated first normal form. Also, why, when we have these composite attributes like name made up of first name and last name, we would keep two columns, first name and last name, instead of having a column name where we'll keep both first name and last name. Unless, of course, this name, because it is a composite attribute, we can always get the name out of first name and last name by concatenating the values in those columns for any row, with maybe a space in between or whatever you want. So that was about first normal form, and then we talked about this concept of functional dependencies, what they mean, and how using functional dependencies we can come up with this notion of different normal forms. Specifically, we have looked into BCNF and 3NF, and also what we have seen is that uh, these other than functional dependencies, the concept of multi-valued attribute is also something that we have to keep in mind. And we have seen that even though there could be schemas which are in BCNF, because of this multi-valued dependency, we need to come up with another normal form, which is the fourth normal form. And for decomposition of schema which is not in BCNF, as we derive the decomposed schema, if there is this property of dependency preserving is not satisfied, and if we want to ensure that dependency, it should be a decomposition should be dependency preserving. In that case, the point is that BCNF decomposition is not always going to guarantee this preserving dependency in the decomposition. And then if we are willing to relax it a little bit and go for 3NF, so 3NF decompositions are always going to be dependency preserving. So that is what we have already studied, and we said that it is with respect to given set of functional dependencies F on a schema R, and these BCNF definition, these are all with respect to the closure of F that we denote as F plus. And we have seen how to compute the closure of a given set F of functional dependencies, which we have seen that we can repeatedly apply Armstrong's axioms and can generate all the possible functional dependencies that would be in F plus using this simple algorithm. So this is what we had studied till yesterday, and a few more points to wrap up this topic. This is about, there are certain additional rules beyond Armstrong's axioms, which are also fairly straightforward, that that also can be that can be, first of all, inferred from Armstrong's axioms, and also we can actually use those as well for generating our F plus. One is that if alpha to beta holds and alpha to gamma holds, then alpha to beta gamma holds, which is fairly easy. So this is the union. Similarly, the reverse of it, that if alpha to beta gamma holds, then of course alpha to beta and alpha to gamma holds. Okay, so which is simple, means that if I fix the value of alpha, the value of beta gets fixed, and also gamma gets fixed. So we can write that as alpha to beta gamma, which means that if alpha is fixed, both beta and gamma are fixed. Similarly, if alpha is fixed, both beta and gamma are fixed. So that means that for alpha, beta is fixed and gamma is fixed. And a pseudo transitivity, that if alpha to beta holds, and if we now have this gamma beta to delta holds, this is very useful. We often apply it. So basically, gamma along with beta functionally determines delta, and alpha functionally determines beta. So alpha along with gamma will functionally determine delta, because we can understand that alpha, we can apply some of the previous rules that to get this, that alpha to beta holds and gamma beta holds. So we can say that alpha gamma beta to delta beta delta will hold, and then we can make out that alpha gamma to delta will hold. Okay. And this can be inferred from Armstrong's axioms, and these are very commonly also used. So let us take a look at one example to make things clear. So you see that we are given this schema R with these attributes A, B, C, G, H, I, and we are given, again the term I am using, we are given, so that means somebody has told that, oh, you see that if this is the complete schema, it has to have this functional dependencies which are specified in the set F. Okay, and as you see that we have a quite a variety of functional dependencies. Okay, now we compute here. We are not computing the complete F plus, the closure of F, rather some members we are showing that because we have A to B, so here A, B, these are columns, okay, column names. So because we see that from the first FD and the last FD, A to B and B to H, by transitivity, we get that A to H also holds. Now, we also see that A to C holds, and if we augment with G, then AG to GC also will hold, GC or CG. And we already now have CG to H and CG to I. So what we get is that we get from A to C through augmentation, we get AG to CG. Now AG to CG and CG to I, these by transitivity we get AG to I. Okay. So similarly, through other approaches also, you can see directly if you can do it with pseudo transitivity and all. Similarly, CG to H is there and CG to I is there. By union, we can get CG to HI. Okay, and so there are different ways of showing the same thing by union or by other methods. As you see that using those rules, we can actually use some of the rules here, and because these are can be inferred from Armstrong's axiom, so only by applying Armstrong's axioms also you might get it, but it might take more time to apply, or more steps to apply Armstrong's axioms, and you might instead apply these quickly, because these are anyway derived from Armstrong's axioms, so that you can get these and get some members of F plus. Okay. Also, you see that here, suppose we are given this A, B, A, C, C, G, H, C, G, I, B, H, and then what you can do is that you can see that out of these, now, if we can, through application of these Armstrong's axioms or the additional rules, if we can get to a situation where a set of columns on the left functionally determine all the columns which are there on the right, then you understand that those which are there on the left form a super key. Okay, so you can try to do that from here also, and if no proper subset of that set of columns on the left is also a super key, then that set of columns become a candidate key. Okay, so that is how you can actually get also what are the super keys, what are the candidate keys, and so on. So, for example, if we compute the entire F plus, which of course is not easy when we have so many attributes in the schema R, but one can keep working on it, and then once you get this all the columns on the right for say, so this F plus contains say 100 FDs, and out of these, if 10 have all the columns on the right, so that means that the columns on the left for each of those 10 functionally determine the entire schema R. So each of them is a candidate. Sorry, each of them is a super key. So it should be clear it is a super key. And from there also see that for any of those super keys, if there are out of those 10, for some their subsets are also super keys, then of course the ones which are supersets, those will not be candidate keys. And the ones for which the right hand side is the entire schema R, and columns on the left, mm, they are of course super keys, and if they do not have any proper subset which is also super key, then you know that those are all candidate keys. So you can end up having, say, 3 candidate keys for the schema R under this set of functional dependencies. F, of course, remember that from F we have to get F plus and derive these 6. So that is how for any R and given set of FDs, you can just by looking at it, you may not know which are the super keys or which are the candidate keys, but you can actually derive the F plus, and from there you can figure out which are the super keys and candidate keys. And again, remember that as I said again for this particular example, so suppose there is schema R. This means not the one on the slide. So suppose there are 100 FDs in F plus. So initially there might be 20 FDs given in F. From there we can derive 80 more and we get F plus. So we from F plus, we as I said that I can derive which are the super keys, say 10 are super keys, and then which are the candidate keys, say 3 are candidate keys. And as you remember that out of the 3 candidate keys, we have to define only one of them as the primary key when we create a table corresponding to the schema R in our database. And for the other two, we can define unique constraints, that the combination. So if column C1, C3, and C7, they are or a combination of columns, maybe C1, C2, C3, C7. They are candidate keys, whichever way it is. So we have to define unique constraint for those columns. Okay. And suppose only C2 itself is a candidate key, or the combination says C2, C9 is a candidate key, which you choose to make primary key. So you will define that as your primary key for the table corresponding to the schema R. The other concept is, so what we have seen is that closure of a given set of functional dependencies. The other is given what is called the closure of attribute sets. So we have been given a set of attributes alpha. Okay, we define the closure of alpha under F, denoted as alpha plus, as a set of attributes that are functionally determined by alpha under F. Okay, so what is important is that we have been given alpha under F, and then we are trying to figure out which all are functionally dependent on alpha. Okay, so for that, what we have to do, we have to compute what is called the closure of alpha. So it is very simple that I find that based on this F and applying the Armstrong's axioms and these rules, for example, if we get, say, alpha to beta and alpha to gamma, then alpha to beta gamma, so this will be also in alpha plus. Okay, alpha plus will have whatever is there in alpha, and along with that, what others are functionally dependent on alpha. So that entire set is called alpha plus. So as you can see that in this example, if alpha to beta and alpha to gamma are there, then alpha to beta gamma will be there in alpha plus. Of course, alpha to beta and alpha to gamma also will be there. Okay. So likewise, by applying this, so it is very simple. We apply similar concept and get which are the ones which are they are in alpha plus. Okay. So we have again an example. So so first is that if we want to get AB, so this is the FD that is given to us, and we are trying to compute AG. Okay, so of course the starting alpha plus is AG itself, and then we can see that we get A to B and A to C. Okay, so then we get A to BC. Okay, and so AG also of course will be GBC, and then AG with B and AG with CG. So we have this AG to ABCG. And now when we have ABCG and CG functionally determines H and CG functionally determines I, so from there we'll also get AG to ABCGH and AG to ABCGHI. And what you notice here is that you see that for AG plus we get the result as ABCGHI, and ABCGHI itself is R, and that means that ABCGHI is functionally dependent on AG, and that means that AG is a super key. Okay, but whether AG is a candidate key, so if A also functionally determines ABCGHI, then AG cannot be a candidate key, and either if A or G are also super keys. But if not, then of course AG is a candidate key. And here you can figure out if you try to compute A plus. Okay, so from A plus, you will see that from A I get B, I get C, so I get A to B C, and because it is B to H, so I get also that A to H, and that means that I get A to B C and H, means I from A I get B C H. But you cannot get this G or I from A, because A functionally determines BCH, but anyway you cannot augment it with G. So we can figure out that A is not able to functionally determine all A, B, C, G, H, I. That means A is not functionally determining R, and hence A is not a super key. Similarly, from G, of course, you cannot get to anything other than what is there is no functional dependency where G is on the left hand side. The one with CG, from there you cannot cannot infer anything about G. So you figure out that G is not a super key. So out of AG, you see that none of its proper subsets A or G are super keys, and hence AG is a candidate. So you see that that is the simple reasoning that you can use to determine by computing the attribute set closure, whether that attribute set is a super key or a candidate. Okay. So, so this is what I have explained. Okay. So, as I just now said, that the uses of attribute closure, that you can test for a super key, as I have just now said, and also to check if a functional dependency alpha to beta holds. So you can check whether beta is in the attribute closure of alpha. Very simple. So that is, we compute alpha plus by using attribute closure and then check if it contains beta. So that is something that you can check whether an FD indeed holds on a scheme. Okay. Um, so for each gamma belonging to R, so you see that you can use the attribute closure to compute the closure of F itself. Okay, that is, you can compute F plus from alpha plus. That means for each gamma which is subset of R, we can find the closure of gamma plus, and for each S which is a subset of gamma plus, we output the functional dependency, that is gamma functionally determines R. And from there, of course, you can get all those FDs which are there in the closure of the given set of FD, capital F. That means from all these alpha plus, actually they will be there in your F plus. Okay. So you can compute the F plus by computing alpha plus for individual set of attributes of the schema R. Okay. Now, if we go back and take a look at this lossless joint decomposition. So, if you see that we said that if we do a lossless joint decomposition, then from the decomposed schema, if we do a natural join, we should get back the original set of tuples in the combined relation. Okay. So if we make incorrect types of decomposition, again, just for your just so that you remember it correctly, I am going to that one here. So this was a an example which was not a lossless joint decomposition. Okay, because you see that we had decomposed it with respect to this name which was there in both the schemas. Okay, if we had done it with ID, ID name, city, street, salary, so if we did it with ID, of course, it would have been lossless joint decomposition. Now, with respect to FD also, we can define what is this lossless joint decomposition, or when decomposition will be lossless. So, suppose we have this schema R and we decompose it into R1, R2. So, what we need is that we need that for all possible relations R on schema capital R, if we get their projections on R1, that is pi R R1, and then their projections on R2, that is pi R2, then natural join of these should get me back the R which was there in the original schema. So a decomposition of R into R1 and R2 is lossless join if at least one of the following dependencies is in F plus. That means that R1 intersection R2, that means the columns that are there in both R1 and R2. It is very simple. R1 intersection R2 means the columns which are there in both R1 and R2. So those columns, either they should functionally determine R1 or they should functionally determine R2. If so, then they will be the decomposition will be lossless, and this is sufficient if we are only talking about functional dependencies and not having multi-valued dependencies. So let us look at this example. So what we have is that we have RABC, and these FDs are there, A to B and B to C. So suppose we decompose R into R1 AB and R2 BC. So what is R1 intersection R2? It is B. Okay, and of course that B functionally determines C, so B will also functionally determine B. That is trivial. And if it is B determines B and B determines C, then by union B determines BC. So we see that it means that B determines BC, and which means B determines R2. So that means R1 intersection R2 functionally determines R2, which we see here. R1 intersection R2 either should functionally determine R1 or functionally determine R2. So we see that it is that B to BC, okay, that is lossless joint decomposition. Also, it is dependency preserving, because we have this A to B and B to C. So these you can actually check in this A to B, you can check in AB, and this B to C you can check in BC. Now, if we look at this other example, that R1 I decompose into AB and AC. So R1 intersection R2, R2 is A, and A functionally determines AB. That means A functionally determines R1, means this is also a lossless joint decomposition. But you see that in this case, that cannot check that B to C. So because that B to C you cannot check either in R1 or in R2. Okay. Without computing R1 natural join R2. So that means that this is an example which is a lossless joint decomposition, but it is not dependency preserving. Again, going back to this example, that if you had seen this example, we have this R1 is ID name and R2 is name, street, city, salary, and R1 intersection R2 is a name. But of course, a name can get repeated, okay, for different IDs. So that means that this name does not functionally determine either R1 or it, and also it does not functionally determine R2. And hence, this decomposition is not satisfying the conditions for lossless joint decomposition. And hence, this decomposition is not lossless. That is, it's a lossy decomposition. And what we had seen previously through this example, now we can understand why it is actually lossy. And again, as I said, that for some of these, it is fairly simple. You know that this name can repeat, and it's easy to understand that joining on name will get back or give back more number of rows. But for, as I said, that if we have these schemas like this, where there are so many FDs and you do not know what is what, So you cannot just go by intuition. Okay, so you need to actually follow this formalism, and we can figure out that whether that is going to be lossy decomposition or it is going to be dependency preserving one. So dependency preservation. So let Fi be a set of functional dependencies in F plus that include. So we are talking about F subscript Y that include only attributes related to Ri. So we have a decomposition of R into Ri, I equal to 1 to n. Okay. So we have R1, R2, Rn, and what is important is that we want to see whether this is dependency preserving or not. So it is very simple. What we do is that we get the set of functional dependencies in F plus that include only attributes in Ri. Okay, so Fi is the set of FDs that include only attributes in Ri. So whatever is related to Ri, we look at that. And Fi is called the restriction of F to Ri. And a decomposition R2, R1 to Rn is dependency preserving if the closure of this union of Fi's is same as the closure of F. So that is very simple. So F1 union F2 up to Fn. So the closure of that, if it is same as the closure of F, then it is dependency preserving. Now, why? What does it mean in plain English? It is very simple. That what we can do, these FDs that we are talking about, this Fi means whatever we can check. So Fi's are including only attributes in Ri. So that means that all these FDs in Fi we can check in single relation Ri. Okay. So F1 I can check in R1, F2 I can check in R2, Fn I can check in Rn. Now, if that means that these are the ones that I can check in each of the individual decomposed relations, and whatever I can check through them, their union uh, means that this is the total set of functional dependencies that can be checked by using a single relation each. Okay, and then if I take a closure of that, if that means that if these are holding, their closures are also going to hold, because the ones in the closure are all logically implied by those which are there in this union. So if that's said, means that all the FDs that can be that are there in the closure of the union of the FDs that can be checked by using single relation if. So if that matches with the closure of the original F, so that means that we wanted to ensure that all the dependencies in F plus can be checked. And what we have said through this F1, F2, Fn is the ones that can be checked on individual relations. And the closure of the first one, that is F1 U2, F1 union F2 union Fn, the closure of this union, if that is same as the closure of the original F, then we are done, because we have to check for all the FDs in F plus. What we are doing is that by taking them on single relations, we know that if they are all holding, then they are, and their union closure is same as the closure of the original set F, then we are done. Means by checking these FIs on individual relations RIs, we are guaranteeing that the original FDs in F plus also was going to hold. And this is the same thing that we are doing. Okay. So let us take one more example. We have this one. We look at this example that we have simple R equal to ABC and F is A to B, B to C. Okay. So you can see that very simply that out of these A to B and B to C, we find that because I have A to B and B to C, so that means A to C also holds. Okay. So basically in F plus I have A to B, B to C, A to C. Out of these three FDs in F plus, okay, the one which is B2C, we can figure out that for that B2C, B is not a super key. Because B is not a super key and it is not a trivial functional dependency, then we understand that this relation schema R, ABC is not in FD. I'm sorry, not in BCNF. Okay. I am repeating that it is a very simple example where I have R equal to ABC and F is having two FDs, A to B, B to C. From there, I can get F plus, which is also going to have this A to B, B to C, as well as A to C. Out of these three FDs in F plus, A to B and A to C, they do not violate the BCNF condition because A is a super key. But B to C, this FD is violating the condition for BCNF. So then what it means is that R is not in BCNF. And we decompose it. If you remember, we have to have this simple formula. Let me go back for your understanding. Yeah. So what do you have? You have to decompose R into alpha union beta, and the other relation will be R minus beta minus alpha. Alpha union beta and R minus beta minus alpha. Okay. So what you do here is that you simply have this B2C is having the problem. So that means that alpha union beta is BC, and R minus beta minus alpha means ABC minus this C minus B. That means ABC minus C. That means AB. So you get R1 equal to AB and R2 equal to BC. And you can now figure out that this R1 and R2 are in BCNF. Okay, that A is a super key on there, B is a super key, and it is lossless joint decomposition because this intersection of R1 and R2 is B, which functionally determines R2, hence it is lossless joint. And dependency preserving means if we see the ones which you can check in each of them. So F1 will be A to B and F2 will be B to C, and union of that is A to B, B to C, and closure of that union is again A to B, B to C, A to C, which is the closure of the original F. That is very simple. Okay. So you see that this is how you decompose. But had it not been the case, then we might have required, as I mentioned yesterday, one more level of decomposition and so on. So testing for BCNF, it is simple. To check if a non-trivial dependency causes a violation of BCNF, compute alpha plus and verify that it includes all attributes of R, that is, it is a super key of R. So a simplified test to check if a relational schema R is in BCNF, it suffices to check only the dependencies in the given set F for violation of BCNF rather than checking for all dependencies in F plus. If why? If none of the dependencies in F causes a violation of BCNF, then none of the dependencies in F plus also will cause a violation of BCNF. But a simplified test using only F is incorrect when testing a relation in a decomposition of R. So whenever it is testing in a schema that is given to us to start with, so there it is fine. But when it is on a decomposition, so consider we have A, B, C, D, E, and we have F is A to B and BC to D, and we decompose R into AB and ACDE. So of course, why we are decomposing? Because you can see from A to B and BC to D that A is not a super key. So A to B is violating the BCNF property. Also, I'd like to mention that if there are two such FDs which are violating the BCNF property, you can start with any one of them for doing the decomposition. So BC to D also we see that it is violating BCNF property. So while decomposing, you could have started with decomposition using BCD, and then the other will be ABCE. But here in this example, we try to do the decomposition using A to B. So one will be having A to B, the other will have ACDE. So now, neither of the dependencies in F contain only attributes from ACDE. Okay, that means that the two FDs A to B and BC to D, they do not contain only attributes from ACDE. So we might be misled into thinking that R2 satisfies BCNF. But you see that in fact the dependency AC to D, because from A to B, BC to D, when we compute F plus, we'll get this we can say that AC through augmentation, AC will functionally determine BC, and from that augmentation AC to BC and BC to D will get AC to BCD or AC to D. So this AC to D, so this is an FD in F plus, which can be checked only from R2. And so we see that AC to D is in F plus, but AC to D here, AC is not functionally determining E. So that means that AC is not a super key, and hence R2 is not in BCNF. So That means that from AC to D, again we'll have to decompose into one will be ACE and the other will be ACD. And then again you have to check whether that is satisfying the requirements for BCNF. So testing decomposition for BCNF to check if a relation Ri in a decomposition in BCNF, either test Ri for BCNF with respect to the restriction of F to Ri. So that is what we have said, or use the original set of FDs F that hold on R, but with the following test that for every set of attributes alpha which is there in Ri, now you can do it simply by checking for alpha plus the closure of alpha either includes no attributes of Ri minus alpha or includes all attributes of Ri. So it is very simple that either it is a trivial functional dependency or it is a super key. So so then that means that if this is violated for some alpha to beta in F, then the dependency alpha to alpha plus minus alpha, that means the ones which are determined by alpha excluding alpha, which are there in that particular decomposition Ri, holds on Ri and Ri violates BCNF. So that means that we have determined which of the functional dependencies are violating the BCNF condition, and that is the one we will use for decomposing Ri. So this is exactly what we did in this example. This is just a generalization of that. So putting that the BCNF decomposition algorithm, which is actually this is only written in a formal pseudocode that we have that initially the result is R, and we compute F plus, and then so for any schema in Ri in result that is not in BCNF, so we'll keep on doing the decomposition. So the non-trivial functional dependency that holds on Ri, and that is not a super key. So that means that we basically have this result minus Ri, means that Ri which is there, that is what we'll remove. Okay, and we'll add the one which is R1 Ri minus beta union alpha beta. So that is basically simple to say that, as we said that for example, from R you first decompose R1 and R2, and we see that R1 is in BCNF because A to B FD holds means A is a super key of R1. But as is shown here, say R2 is not in BCNF. Suppose I decompose R2 into R21 and R22. So then I will not have R2 anymore in the result set, but R21 and R22, and if both of them are in BCNF, the result will be R1, R21, and R22. So that is exactly what it is saying, that you are removing the result Ri. That means you are removing the R2, and you are now adding that R21 and R22 in the result set. I gave a similar example yesterday about decomposing R into R1 and R2, if you remember. And one of them is in BCNF, so I decompose the other one into 2, and then if required, we'll decompose the one which is not in BCNF once again. So here is this nice example of this, that again that A, B, C, A to B and B to C. So key is A, R is not in BCNF, so B to C, but B is not super key. We decompose it to BC and AB. So which we have seen already before that, but now it is exactly following this algorithm. So we have another example of BCNF decomposition. We have this relation. Now see that we have a complex schema R class having these many attributes, and these are the functional dependencies which are defined. Okay, so we see that there are a lot of FDs, and we cannot intuitively say what is the correct decomposition and all, but we can figure out that course ID along with section ID, semester, year. Okay, so they so you see that from course ID I get title, department, credits, and from course ID, section ID, semester, year I get the rest of the column. So course ID, section ID, semester, year is a candidate key of this schema class. So but of course there are so many like this. We are having course ID to title, department name, credits. So where course ID is not a super key and it is not not a trivial FD, so we have to do a decomposition. So we are using this one, as I said, that course ID to title holds, but it is not a super key. We replace class by course, which is this one, alpha union beta, that means course ID, title, department name, credits. The other is alpha minus beta. So class one, that means that we have to get rid of this title, department name, credits, but the rest of it will be there. So it is course ID, section ID, semester, year, building, room number, capacity, time slot ID. So but the course is in BCNF, which is trivial. We can figure out that we have this functional dependency from course ID to these things, and that means course ID functional determines all the columns. So course ID is a super key, hence course is in BCNF. The other one, that is this in class 1, class hyphen 1, this building room number capacity, which was there, you can see that building room number capacity is the second FD in the second bullet. So that holds, but that is not a super key. So now I have to decompose this class 1 into two, classroom and section. So classroom has building room number capacity. So the only FD that holds there is building room number 2 capacity. So that means that classroom is in BCNF, and this course ID, section ID, semester year, building. So we have got this course ID, section ID, semester year, building room number, and time slot ID. So both of them are now in BCNF. So this decomposition. Finally, what are the schemas we'll have in the final decomposition from this original class? We'll have one called course, one will be this classroom, and one will be section. Of course, that class hyphen one, that will not be there in my final set of schemas. Okay. So, so that is what I think this got messed up a little bit. I think this arrows came here, but anyway. Uh, so next is about the multi-value dependencies. Let us take a short break, and we'll come back and discuss that part and complete this chapter. So it is 10:49. So let us take a break for 10-11 minutes. So let us come back at 11, and we are left with about 8 more slides. So we'll come back and complete it. So let us meet at 11. Okay, so welcome back. We'll resume our discussion, and there are only a few things that are remaining. Just give me a second. Okay, so let us resume our discussion. Okay, and I think I have to again share my screen. Okay. So up to this, we have talked in detail about these functional dependencies. Now we'll look at multi-valued dependencies, which already actually we have discussed, but it is only putting it in again in the perspective of these functional dependencies. And not, I'm sorry, not functional dependencies, the dependency, and then how we do the decomposition, which is actually fairly easy and based on our understanding of multi-valued attributes in the context of ER diagram, it is actually derived from there. So this multi-valued dependency is written in this form alpha and then this double arrow beta, okay, holds on R. If in any legal relation R of R for all pairs of tuples T1 and T2 in R, such that T1 alpha is equal to T2 alpha, there exists tuples T3 and T4 in R such that T1 alpha equal to T2 alpha, which is equal to T3 alpha equal to T4 alpha. T3 beta is equal to T1 beta. T3 R minus beta is equal to T2 R minus beta. That means that these for the columns in beta, they match in T3 and T1, and the columns which are the rest of R not in beta, that means R minus beta, that match in T3 and T2. Similarly, the other way, that columns in beta match between T4 and T2, and columns in R minus beta that match in T4 and T1. Now, what it means, it is, if you take this example we had seen before, that we have this employee code and then this child's name and then the phone numbers. So if you simply take these T1, T2, T3, T4, so we see that this alpha, okay, so there is this multi-valued dependency alpha to beta. So if we look at this example, that alpha is this 99999. So this is this column for that. So maybe the ID. So that is matching between all of them T1, T2, T3, T4, and T3 beta equal to T1 beta. So you see that this 512555123 that number is matching between T3 and T1, and the other aspect, that is R minus beta, okay, so that is between matching between T3 and T2. That means this William you see is there in both T2 and T3. Similarly, T4 beta, so if you see that T4 beta that is matching with T2 beta, that means this phone number 512555432T1, it is matching between T4 and T2, and the rest of it, that is R minus beta, is basically this column for the name of the child, and the value David, it is sent in T4 and in T1. That is all it says. Okay. So in the tabular representation, so basically now instead of having a single column, alpha is basically a set of columns. So that is what they are denoting as A1 to AI, and beta is a set of columns AI plus 1 to AJ, and R minus alpha minus beta is AJ plus 1 to AN. So assume that A1 to AN, these are the columns in the entire schema R. So this is a generalization of this single column example that is shown here. So in our example, we have these two multi-valued dependencies. From ID, there can be multiple child name, and ID, there can be multiple phone number. So, so that means that it is supposed to formalize the notion that given a particular value of Y ID, it has associated with it a set of values of Z, that is the child name, and a set of values of W, the phone number. And these two sets are in the same sense, in some sense, independent of each other. So child and phone, so they have no relationship. Okay. So now to ensure fourth normal form, decompose the schema R so that ID child name is in one schema R1 and ID phone number is in another schema. So there is very simple one. Okay, and it can be shown that any schema in fourth normal form is also in BCNF. So this is a higher normal form as compared to BCNF. So this is the simple understanding of a multi-valued dependency. But of course, we now put it in the terms of this dependency. Of course, it is again, remember, it is not functional dependency. It is what we denote as multi-valued dependency. So there are indeed other higher normal forms like joint dependencies and so on, which is called, there is something called project joint normal form, also called fifth normal form, and domain key normal forms, and so on. Okay. The issue is that it is not so easy to reason with them, and no set of sound and complete set of inference rules exist. So hence these are rarely used in database schema design. So to summarize, what we will do is that we will effectively be restricted to this BCNF, and for multi-valued dependency we will go for fourth normal form. And for decomposing a schema which is not in BCNF, if we want to ensure that dependency will be preserved, then BCNF decomposition may not always guarantee that. Hence, we may relax it a little bit and go for 3NF decomposition. But otherwise, we can go for BCNF if we do not care about dependency preserving. And whatever decomposition technique we follow for BCNF decomposition, or if we do go for third normal form, those decompositions are always lossless. Okay, so we do not need to worry about that. But if it is BCNF decomposition, we have to keep in mind the dependency preserving property. So that is what we need to worry about. So overall database design process, if we see that actually I just now mentioned the same, that we have assumed the schema R is given. Now this is very important, and I will connect it to the next two slides. Here we are assuming the schema R is given. So R could have been generated when converting yard diagram to a set of tables. R could have been a single relation containing all attributes that are of interest, often called a universal relation. A normalization process, as we have studied, it breaks R into smaller relations. Okay, so R could have been the result of some ad hoc design of relations, which we then uh, test or test for whether BCNF property holds or not, and convert to normal form. So if you again see this one, that the first one that was given to us, so this was someone gave to us, right? We assume that this is given, and we said that if this is there, okay, so then we want to break it up into smaller relations. Okay, so if you see this, that suppose we are suppose we combine this and we get this. Okay, so that means someone is giving to us, and which we do not always know whether it is a good design or bad design till we are given the functional dependencies properly. Okay, now so this is what we said, that not all decompositions are good. So we want to decompose it. Okay. So we said that we started with this, and the slide is how about smaller schemas. Okay. Now smaller schemas, of course, means that from this original one we'll get schemas with lesser number of attributes. Okay. So we wanted to get smaller schemas, but now in the whole process we have studied that these smaller schemas, if we try to do arbitrarily like this type of decomposition, we'll end up getting lossy decomposition. Of course, this is something that is not acceptable. But even if it is not lossy, we have to ensure that we first understand that this is not exactly good design, and what is a good design, which is what we have studied all the way. And based on that, we now know fairly well that we are given a schema. Now coming back to this step, we are given a schema, then we would check whether that is satisfying, say, the BCNF property or not. If not, then normalization is used to break R into smaller relations. So this is important. The smaller relation is not obtained in an ad hoc manner, but using the proper normalization process. and then we check it and do the actual process of our database design. Now here you might have a doubt. Okay, so if we see that in chapter 7, which we took up right after our chapter 1, we talked about ER model, and from ER model we have learned how to get the database. Okay, now you might question that, oh, if you do it like this, so we do not get the initial schema in an ad hoc manner, but we do it, we generate it by following this database design process starting from an ER model. So first point is very, very important, that when the ER diagram is carefully designed, like we have appropriately identified the entities, their attributes, and then their relationships, multi-valued attributes, weak attributes, and so on. Sorry, weak entities and so on. Then, if we follow that method for generating database schema from there, uh, and we follow the rules properly, like you do not end up like for a many to many relationship, you do not have that third table, rather you try to push it to one of those sides, then you have made a wrong design. And that wrong design, actually, if you do, you will see that that will violate your normalization principles. Okay, so that database, this is very important, like translating uh, an ER model to a database schema, that particular uh, process, there it is already ingrained that what you will get out of it, if you follow it correctly, those will be already in appropriate normalization, like they will all be in BCNF. So they should not need further normalization unless you have made a mistake either in the ER diagram, where you possibly did not capture or the attributes properly, something you made as a key attribute which is not supposed to be key attribute, and so on. Then the schema that you would get might violate normalization. Or if you have a correct model but your translation to the schema is not done correctly, then you might also not get these relations, the schemas in appropriate normal form, like BCNF, or multi-valued dependency, like not in fourth normal form, and so on. So if you have done everything correctly, you would not need any further normalization. That is something you have to understand. Okay, but as he says that in a real imperfect design, there can be functional dependencies for non-key attributes of an entity to other attributes. So there are these department name and building, and a functional dependency department to building. So the good design would have made department an entity which you did not do properly. Okay. So, if not, then if everything is done correctly in terms of modeling and translation into schema, you will by default or by design you will end up getting schema which is in BCNF. So, functional dependencies from non-key attributes of a relationship sets possible but rare. Most relationships are binary, so so because most relationships are binary, so usually you will not have any problem. But otherwise, if you remember, we talked about this ternary relationship where you have multiple arrows coming out, which can have ambiguity and all. So there you might end up in schemas which are not in BCNF. So then you have to test for this BCNF. But if not, you will be good and you don't need to do it. That's why we studied the ER modeling first, and also how to get your database design, because sometimes you can have but even then we studied the normalization, all this, because now you know what is a good design, what is not a so good a design, and what actually we have already achieved through your modeling approach is a good design. And furthermore, if for example you start, and many of the times if you suppose start working in a project, okay, and maybe there is a lot of legacy code, and that is what can happen if you go to the industry. There's a lot of legacy code where maybe the modeling was not done properly, or it was initially done and then over the period of time a lot of ad hoc changes took place in the schema. And now when you join the project, you are given a schema having, say, database schema having 100 odd tables, and for each table there are, say, 20 columns or so. You might be at a loss. Okay. So in order and then your job might be to check whether this is a good design or there are redundancies because we are getting some inconsistencies and all. So then first thing that you need to know is to somehow articulate the set of functional dependencies. Okay. So somebody will have to give the actual functional dependencies that are assumed, or the users will verify whether the what are the FDs on those tables, and from there you can start looking at and now follow these steps that we have studied in this chapter to see whether indeed the design that currently exists in the system is a good design or it is not so good a design, and then if it is not so good a design, how you can make it a good design. Okay, so that is the learning that you have from this chapter. And if you start a project afresh, then of course there is no schema given to you. You just have some initial user interactions like SRS diagram and all, where you have to also have the ER modeling done, get it checked by the users, and from there you will translate the entities, relationships, etc. Into your schema. Okay, so that is the whole process that you have to keep in mind. Okay, so that you can actually follow the things systematically, either from scratch or you join in the middle. Further, the last point that we are so far talking about normalization, it is good and all. There are certain instances where, okay, so let me tell you something that if you go to this example, so if of course it is not a good design, but in order to get information about say the building where say Einstein sits, so from Einstein's department name physics, you can get the building name Watson from this table. You don't need a join. But if you break it up into two tables, one will have ID, name, salary, department name, the other is department name, building, budget. Then if I want to get where does Einstein sit, I have to join the two tables to see that the physics department is located in the Watson building. Okay. So, of course, whenever everything is there in one, there is a chance of inconsistency and all. But of course, the selects are going to run faster because you have everything in one table. You do not need joins. And as we have seen that if you decompose any relation schema into say two, and then they are not again one of them is not in BCNF, you again decompose further, and you get three, four, five relations from starting from a single table. Okay, as we saw for those cases. Okay, so like this one, we if everything we wanted to get from class, now I will not need any join. Okay, but now we are replacing it this class to course and then classroom and section. So if I want to get the information, I may have to join multiple tables. So when you are actually having a large number of tables and your queries are complex, which span multiple tables, okay, then you may have to join two, three, four, multiple such tables in order to get back the result. Okay. Now, when indeed there is a lot of data in the tables and there are many tables to join and the queries are complex, then having exact normalized design will result in slow query response, especially when the query response is important. So there are sometimes reasons that we would do some denormalization uh, purposefully for performance improvement. Okay. So we have seen these examples that join with prerequisite to get the course ID and all. So what we can actually do is that we we can selectively denormalize things. Okay, that we can use denormalized relation containing attributes of course and prerequisite with all the above attributes for faster lookup, but it will mean extra space and extra execution time for updates will have to be done carefully, and for the programmer extra coding work and possibility of error in extra code. Now and the other option is that use a materialized view. So where, as you have mentioned before in the context of view, that we may want to do those joins, okay, and create a view, and then we materialize it, and in that materialized view we keep the data. Okay. Now, when it is materialized view, remember we said that then we have to ensure that whenever the underlying tables are updated, the data in the materialized views are also updated. Now let me tell you something, and which is something we'll study in our next week's lecture. So next week there will be no lecture, no lab, and and after that next week, of course, on on the 22nd we'll have our test. Now after that we'll take up the topic what is called data warehousing and data mining, where we'll see that we actually go for denormalized design. Okay, and the reason is that there in data warehouses the queries are indeed very complex, as I just now had mentioned, which span multiple tables. So if you try to actually join so many tables on the fly, it might become slow. So you may want to go for denormalized design there. Okay. But then you might ask that, oh, if you go for denormalized design, so far we are talking so much about normalized design, because with denormalization there might be some these inconsistencies and so on. Okay. Now when we get the data warehouse, as we'll study there, that this data warehouse, the data in the data warehouse tables, these are not updated through individual users screens. Okay, rather there is a controlled process which is called ECTL process: extract, clean, transform and load. And this process actually will have it automated that which all tables data will be collected. So you'll see that there is an online transaction processing database and an online analytical processing database, or a data warehouse database. So in a controlled manner, only data is pushed from normalized tables to denormalized tables. Okay, so that the chances of inconsistencies creeping in due to individual individual insert, update, delete, that will not occur. Okay, so what we'll be able to achieve is that we'll be able to achieve higher or faster execution time because of denormalized design, and at the same time there will not be inconsistencies creeping in because the changes are made to the denormalized tables not by individual users but through a very controlled process, which will have everything written in a script, so that the data is loaded in a very controlled manner and it will not lead to any inconsistency. So that is what you will be able to achieve in data warehouse, which will, as I said, will be our next topic in next week, and and that is when you go for selective denormalization. But in the usual database transaction, the transactional database like your ERP database and all this that you are having, or banking, all these applications, uh, in the front end, the database environment, which is called online transaction processing or OLTP environment, these are all going to have normalized design. Otherwise, very quickly they will end up having inconsistencies. That is what we will discuss in the context of data warehouse, how selective denormalization is done. And materialized view, once again, that this as we mentioned, that materialized views will take up a lot of space, okay, additional space, because it is storing the same data in the base table once again in the materialized views, and we have to keep the data in the materialized views up to date. Now how can that be achieved? This can be achieved because, again, because it is done through a controlled process, transferring data from this OLTP database to the data warehouse database. That control process will update the base tables and they will also update the materialized views. Okay, and because it does like that, hence there is no chance of there being like stale data in the materialized views, because the process that updates the data in the base tables, they will also update the data in the materialized views. So there are two things we talked about. One is that we can use materialized views there. So the base tables are normalized, and materialized views are basically through view definition, which are selects, joining the tables, and we are keeping the data there. So the response time will not suffer. It will be sufficiently fast. Okay, and in response time is very important in data warehouse database because they will actually include joins of very large number of tables. Okay, so these are the issues that we need to keep in mind for performance from database design point of view. But once again, to reiterate that there are these two types of databases. The one that we interact with normally in these applications like ERP, banking, airlines, online shopping. These are all OLTP databases, and then they transform data into another database, which we call data warehouse for long term their planning and their decision making and so on, often called decision support systems. So that is another database which is used mainly for querying or only for querying. So there the chances of inconsistencies due to individual changes are very, very low. So that is why there you can afford to make this denormalization in the design. But otherwise, we are focused only with appropriately normalized databases. So that brings us to the end of this discussion. So from this book, chapter 8, you read the book except for the following subsections. Okay, so just make sure that you read this carefully, the instructions. So except for these, you read the other sections and subsections from the book. Okay, so that actually brings us to the end of our discussion on what we wanted to cover before your this mid semester exam week. And up to from chapter 1 to chapter 8 is your syllabus for the test in the coming week, and we'll announce more details about the duration of the test and so on. And it will be, of course, held on Moodle. And the other thing that is important is that so for this lab on Thursday, what I will do is that I will set up a link in Moodle, and through that link, the group leaders will submit the details. So, and that you can do by maybe 5 p.m. on Thursday. Of course, there is no need to meet in the lab, so we are not going to hold a regular class during that time this Thursday. Once again, we wanted to ensure that before your exam week, things are a little less heavily loaded. So it is just that you ensure that your group is formed in that spreadsheet, and you just have whatever is instructed as I will circulate through Moodle link by 5 p.m. on Thursday, and there is no need to actually meet. Within the team you discuss at your convenience. Okay. And in the next week, we are not going to have a class on Monday or Thursday. Tuesday, we will have the test. Okay, maybe we'll start around 10:15 or so that everybody joins from the previous class. And we'll let you know what is the duration of that. Is there any question from anybody? And in the week of next week is 21st, so week of 28, we'll take up topics on data warehousing, data mining first, and then as you, if you remember, I mentioned at the beginning that initial part, this pre-medicine part, is about designing the database, and after that we'll complete it with the data warehouse design, and after that we'll take up how actually in the database management system now things are done in an efficient manner. That is how we index the data, how the data is stored, how it is indexed, how these different operations that we carried out that are handled by the database management system. So those aspects will be covered in the second half of our semester.
Sir?
Yeah.
Sir, I had sent you a mail about a lab evaluation. You had replied to it. So like, will it be done?
This is about what? What was the question?
Sir, about lab question 1 part B evaluation, I had a conflict with the TM. So,
it is we. Okay, I'll see. This is which one? Lab test 1, question B.
the B, yeah, part B.
Oh, I see. I understand. Yeah, I'll look into it. Yeah, I remember that. Yeah. See, what I will do is that maybe a couple of weeks before our semester closes. Okay. So at that time, when you are going to be working on your mini projects only, okay, mini project 1 and mini project 2, and of course the lab test 2. So at that time, whatever these things are pending, will sort out. I mean, whatever is reasonable is what we'll do at that time.
Sure, sir.
Okay.
Thank you, sir.
So you please wait till that time. So tentatively by maybe the third week of March or second to third week of March, we'll work on all these issues.
Sure, sir. Thank you, sir.
Till that time, please hold on. Anything else? Any other question?
Hello.
Yeah.
So for this Thursday, can we get like a little more time for deciding upon the topics? Like maybe till Thursday night itself, like not till 5 p.m.
How will that help? You only have to decide a topic and maybe write a one pager on that.
Yes, so like a little, I
Uh,
just want to research a little bit more, and I don't think I'll have time before Thursday to do that, and maybe 3 hours won't be enough. So
okay, so I mean, I
just
can
till the
always
night.
that is fine with me. I have no problem, but it is up to you to plan your time appropriately. I will do that. So because you are saying that if that helps and it is not in the critical path, we'll do it. But I'm just suggesting that your group members, you have decided your group, right?
I'm doing it alone this time. Yeah.
Oh, you're doing it alone. So that's fine. But those 3 hours actually you can reserve for this work and come up with whatever you want. But anyway, so I mean, it was just a suggestion for your time management. But um, because it's not in the critical path, and assuming that you are having tests etc. coming up, so I will make it. I once I put up, I'll make it till end of the day, midnight on Thursday.
Yes,
Okay.
sir. Thank you. I just didn't want to make a hasty decision. That's all. Thank you, sir.
Oh, sure. That's fine. Okay. So that's good. And yeah, so that's settled then. And so please ensure that the spreadsheet is filled up with your details and of the project. Yeah, that's
Sir, could I please have one more clarification about this mini project? So,
uh-huh.
um, sir, like while writing our program, it is necessary that we make raw SQL calls from our program, right? Like that's a necessity.
I mean, what are the other options?
I mean, say, suppose if I'm using Spring, then
Uh-huh.
I don't actually need to use raw SQL. If I define a class and define say constraints in the within the class and
Mm-hmm.
define an interface for say which type of access I require, then
Mm-hmm.
Spring automatically generates whatever SQL calls are required. So there's no
Right,
need of using any SQL there.
but so what you mean is whether you have to write explicit SQLs, right?
I mean, say like if I'm using something simpler like
Mm-hmm.
SQLite Python that
Mm-hmm.
or something like that. So there we have to write db dot
Right.
transaction get, then get select or get select statements, basically select
Right.
from join that.
Mm-hmm.
But if we use something like Spring, then we don't actually need to write select statements.
I
uh,
understand, but so just ensure, so that is fine. But as long as to use Spring framework, that is okay. But just make sure that you are not doing it, as I said, that finally the evaluation will be relative. So you do not end up writing like one string for one table. So there is nothing that writes to multiple tables or reads from multiple tables. So ensure that it is not simple like only for what table, from table you have a one-to-one mapping with your screens.
I see.
Okay, because see, as soon as you go for multiple tables, somewhere you will have to specify either explicitly as an SQL, or somehow you have to tell it, right, which tables to join
Yes,
on
sir.
which
Like
column. We will
usually
not know.
the way Spring does is that we have to define a class that implements say three interfaces for the three tables,
Right,
and
right,
that
right.
way
Uh,
it
that,
figures
that
out using reflection.
right, but that is what. So it will not figure out. You have to tell him what is going to be joined with what. I mean,
Yes, sir.
in that sense. Okay.
Yes,
So
sir.
that is what is important. That you are not having trivial forms, one for each table. Okay. So that is not going to work. That's
Okay,
the
sir.
point.
Yeah. So that's okay. So like it figures out the SQL, but I need to tell how to generate the SQL.
Yeah, and also as I said that so that is why we have these intermediate deadlines, huh? That you also discuss those things with the TS during the so what we'll do is that for you there will be some say maybe say roughly about 18 to 20 groups. So what we'll do is that we'll assign maybe two or maybe yeah about two or three projects to each TA, and they are going to give you this feedback from time to time. So that's
Sure,
why
sir.
we have those intermediate deadlines, ER model, and then your
Yes, sir.
the progress and so on, so that you can get those things clarified. Yeah, but this is the general guideline from our side is that what we want is that we want to you to have some rich functionality in the first part, and for the second part it is for you to learn the technology how to develop these mobile apps. Okay, so that is the thing we would like you to learn. That is
Thank you, sir.
okay. So I am now stopping the recording, and